Hi everyone. Today in this video we are going to discuss about FTIR spectroscopy, Fourier Transform Infrared Spectroscopy. So what is the principle behind this FTIR? What are the instrumental components? And what is the Fourier transformation? All these things we will discuss in this video. What is FTIR? It is defined as Fourier Transform IR Spectroscopy. So here FT indicates Fourier transform, which is a mathematical conversion that brings an advantage compared with the dispersive IR spectroscopy. So what is this mathematical conversion? In this FTIR, we are converting the time domain into the frequency domain, and this conversion is called as Fourier transformation. The main principle behind this FTIR is the production of path difference between the two optical pathways, which results in the interference which may be either constructive or destructive. And this path difference is directly proportional to the intensity of the radiation which is passing into the sample, and which is then converted into a wave number. In this way, in the Fourier transformation, the path difference is related with the wave number of the radiation that is passing into the sample. And this process is controlled with respect to time. So we can accurately measure the wave number of the radiation passing through the sample. And that makes the FTIR to achieve more accuracy and precision compared with the dispersive IR spectroscopy. So today in this video, let us see the instrumental components and principle behind this FTIR. Similar to the dispersive IR, FTIR also having the source where it produces IR radiation, and this IR radiation is then passed through one of the device that is called as collimator. This collimator makes the radiation parallel to the sample cell, and once this radiation is passing through this collimator, they can go parallelly into the another component, interferometer. We can observe that monochromator is not present in this FTIR. Instead, interferometer is going to be placed between the source and cell. After passing through the interferometer, the transmitted radiation is coming perpendicular to this interferometer, and then it is transmitted into the sample, and finally it reaches to the detector. So these are the instrumental components in this FTIR. So first one is the source. What is the source we can use in the FTIR? Generally we are going to use the mid-IR region. So for mid-IR region, we can use the globar source as well as nearest glare. So these two sources are useful in the mid-IR region, which is from 4000 to 400 cm inverse. And we can also use a tungsten halogen lamp in case of near IR region. And for far IR region, we can use the high pressure mercury vapor lamp. So these are the sources we can use in order to produce IR radiation. Then within the FTIR, important component is the Michelsen interferometer. What is this Michelsen interferometer? This component just acts like a monochromator, but it works by different mechanism. This Michelsen interferometer is mainly having the three important components. First one, it is having the beam splitter, which is going to split the incident radiation into the two equivalent radiation, and it is having the helium neon laser beam, which is responsible for the accuracy in the FTIR. And finally, it is having the two mirrors. One is movable and another is a fixed mirror. So these are the components present in the FTIR, and here beam splitter is made up of germanium coated on the potassium bromide, which can cleave the incident radiation into two equivalent components. So this is one of the mirror, this is the fixed mirror, and this is the movable mirror. Now the source is going to send the IR radiation. This IR radiation is going to pass through the collimator, and it is going to strike the beam splitter. This beam splitter is going to split the radiation into the two equivalent components. One of the component passes towards the fixed mirror, and another component travels towards the movable mirror. And once this radiation is going to strike the mirror, they are going to be reflected. So from the fixed mirror it is going to be reflected, as well as from the movable mirror it is going to be reflected. Now what will be the path difference? Suppose both fixed mirror as well as movable mirror are at the equal distances from the beam splitter, then the path difference is 0. Because the path difference is 0, now the two reflected beams are combined and they are going to be transmitted perpendicular to the interferometer. Now this radiation is passed into the sample, and finally it reaches to the detector. So this is a condition where both movable mirror and fixed mirror are at the equal distances from the beam splitter. But after time t, this movable mirror is going to move. Suppose it is going to move like this. Then what happens? Now the movable mirror is somewhat nearer to the beam splitter. So the reflected beams will have the different path lengths. Because of the difference in their path lengths, there is a path difference between the two reflected beams coming from fixed mirror as well as the movable mirror. This path difference produces a interference within the spectra, which may be either constructive or destructive. And here the position of the movable mirror is accurately measured by helium neon laser beam. This laser beam is going to be passed towards the movable mirror, which can be reflected such that it can detect the accurate position of the movable mirror. In this way, in the FTIR, the position of the movable mirror is accurately measured, which gives the accurate measurement of the path difference between the two reflected beams coming from the fixed mirror as well as the movable mirror. Now the optical path difference is the difference between the path lengths of two optical waves, which may produce the interference in the spectra, and this interference may be either constructive or destructive. What is constructive interference? Suppose we have a wave like this and another wave is like this, and these two waves are in phase. That means they have the similar crests and troughs. Now when they are going to interfere in similar way, they produce a constructive interference such that the net wave will be like this. So here you can see the amplitude is somewhat increased because both of the waves produce a constructive interference. Now let us see the destructive interference. Suppose a wave is like this and another wave is like this. You can see that the first wave is having the trough and second wave is having the crest. So when they are going to interact, they produce a destruction. Then the resultant wave will be like this. Because both crests and troughs are going to cancel their amplitudes, we cannot observe any significant amplitude in the wave. So a constructive interference always increases the amplitude, but the destructive interference are going to reduce the amplitude. Now based on that, interferogram is going to be plotted in the FTIR. So constructive interference is observed at n lambda wavelengths, where lambda is the wavelength and n is the order of interference, and n value may be any integer like 0, 1, 2, 3. Destructive interference is observed at n plus half into lambda. Again, n may be either 0, 1, 2, 3 and so on. So based on this constructive as well as destructive interference, where interferogram is plotted such that amplitude on the y-axis and optical path difference data points on the x-axis, we can get a plot like this. So in this interferogram, the amplitude is measured in terms of volts and the data points are measured in terms of time. That's why interferogram is measured in terms of time domain. This time domain is converted to frequency domain by Fourier transformation. Now in the Fourier transformation, the interferogram is going to be converted such that we can get a plot like this, where the y-axis is the intensity and x-axis is the wave number. So here we can get a plot like this, and this process is a mathematical conversion which is called as Fourier transformation. So in the Fourier transformation, the time domain is going to be converted into frequency domain. So this is called as FT, Fourier transformation. Because wave number is directly proportional to the frequency, commonly it is called as frequency domain. In this way, with every time, a particular wavelength of radiation is going to pass into the sample, by which we can easily observe the IR spectra, where the transmittance can be measured at a particular wave number with high accuracy as well as precision. Detector in FTIR. Since FTIR is highly accurate and precise as well as it's having the high speed of detection, so we have to select the detector which is fast acting. So fast acting detector, otherwise the detectors which are having the low response time should be selected as the detectors in the FTIR. Commonly we have pyroelectric detectors which are made up of deuterium triglycine sulfate, DTGS. Otherwise we can use the photon detectors where the semiconductor is going to be used, which can be filled with the mercury cadmium telluride. So both of these detectors are having the fast response, therefore they can be used in the FTIR. So that's about the Fourier Transform IR spectroscopy, commonly known as FTIR, which is having so many advantages compared with the conventional dispersive IR spectroscopy. In this FTIR, monochromatry is not used. Instead, Michelsen interferometer is used, which is made up of two mirrors. One is of fixed and another one is movable. And it also includes a beam splitter which is made up of germanium coated on the potassium bromide. and we can also use the helium neon laser beam in order to detect the accurate position of the movable mirror. The interferogram is plotted as amplitude versus data points, and these data points are measured in terms of time and amplitude is measured in terms of voltage. This time domain interferogram is then converted into frequency domain by mathematical conversion, which we call Fourier transformation. So with this Fourier transformation, every time a fixed wavelength of radiation passes into the sample, so that we can accurately measure the IR spectra of the samples. And this FTIR also having speed advantage, such that we have to use a fast acting detectors like pyroelectric detector or photon detector.